My name is Marco Coisson and I'm a researcher at the Italian National Meteorological Institute. In this video, I am going to present to you a summary on the techniques that can be used to measure magnetic properties of materials. Measuring the magnetic properties of materials is a difficult challenge because they depend, of course, on the intrinsic properties of the materials themselves, such as the composition or the macrostructure, but also on extrinsic properties such as shape and size. Moreover, the quantities to be measured, such as permeability or coercivity or magnetizing frequency, may span over many orders of magnitude. Additionally, if the measurements are not done in controlled laboratory conditions, but in field applications, the application environment can be very hostile. This means that the technological requirements for the materials may not fit the measuring requirements to do repeatable and of metrological level measurements. When measuring the magnetic properties of materials, it is assumed that you are also able to measure the magnetic field that is applied to the material itself. The techniques used to measure the magnetic fields are covered in a different lesson made by Vittorio Basso that is also available online. But when talking about magnetic fields, we have to consider that there are several different magnetic fields. There are at least three. One is the field that you apply with a magnet, a coil, or whatever, and that is used in your application. Then there are the magnetic fields that are generated by the magnetization of the sample. These are sometimes called the fringing fields, and also demagnetizing fields depending on the condition. And then there is the field that is inside the sample, that is called internal or effective field, that is a combination of the other fields. Let's now have a look at the different magnetic fields. The applied magnetic field is the one generated by a solenoid, a set of coils, or an electromagnet, as in this example. It is relatively easy to identify the applied magnetic field, and it can be measured with several kinds of sensors, such as a Hall probe, as in this example. The applied magnetic field is the field at which the sample is also submitted. Either spontaneously or because of the application of the applied magnetic field, the sample magnetizes, and its magnetization, like that of a dipole or of a permanent magnet, is the source of a magnetic field, of a fringing magnetic field in the surrounding volume. Let's now have a closer look of what happens in the sample. When the sample is magnetized, at its surface appear magnetic poles that we conventionally call north and south. These poles are the sources of the fringing fields that we discussed earlier, but also they are responsible for a different field that again goes from the North Pole to the South Pole as any field that is located inside the material, inside the sample. This field is anti-parallel to the magnetization. Since it is located inside the sample, and because of its direction that opposes the magnetization, this field is called demagnetizing field. Generally speaking, the demagnetizing field is proportional to the saturation magnetization of the material through a coefficient that depends on the sample shape and on the direction of the magnetic field with respect to the shape of the sample. However, this expression is correct only in the case of ellipsoidal samples and in the case they are completely saturated. If that is not the condition of your sample, this expression is only approximate, and an exact calculation of the demagnetizing field is not possible. Numerical methods are required for each applied magnetic field value, and therefore for each magnetization value assumed by the sample in that condition to calculate the demagnetizing field. The situation that we discussed so far is typical of an open magnetic circuit, meaning that there is no continuous path made of magnetic materials that includes your sample. You can tell that this condition is the one of an open magnetic circuit because there is an air gap between the sample and the electromagnet. The other possible condition is the one of a closed magnetic circuit, meaning that there is a continuous path made of magnetic materials that includes your sample. In this example, you can tell it is a closed magnetic circuit because the sample edges are clamped between the pole caps of an electromagnet. Since the sample is clamped in a closed magnetic circuit, there are no magnetic poles at its edges. This, as a consequence, there are no fringing fields outside, and there is also no demagnetizing field inside the sample. This means that it is relatively easy to know the field inside the sample because it is sufficient to measure, for example with a Hall probe, the applied magnetic field. Therefore, which measurement condition has to be preferred? It really depends on the sample that you have to characterize. If you can, stick to a closed magnetic circuit because by simply measuring the applied magnetic field, you know the internal field of the sample. The drawback is that you must be able to clamp the sample into a closed magnetic circuit, so the sample must have an adequate shape and size, and you also have a limited choice of measurement types. Conversely, open magnetic circuits allow you to work with any sample shape, of course not any sample size, but you have also a large variety of sizes that you can play with. You have a wide choice of measurement types, but it is extremely difficult to know the internal field because you must know the demagnetizing field in order to calculate it. And this is, as we said, a very challenging task. So what are the physical principles that we can exploit to measure the magnetization of a sample? The physical principle that is most widely exploited to make magnetic measurements is the Faraday-Neumann-Lenz law, that states that if you have a coil made, for example, by a copper wire that is linked with a magnetic flux, you have an electromotive force, so a voltage, at the coil when that flux varies with time. Indeed, this simple formula is just one law, but is linked to two different phenomena. One, when the magnetic field changes in time or the cross-section of the coil changes with time, and the other case when everything is constant, but the coil moves through a uniform magnetic field. The first case, where either the magnetic field or the cross-section of the coil change with time, is exploited in BH loop tracers, wattmeters, and per millimeters. The second condition, when the magnetic field is uniform, the cross-section of the coil is constant, but the coil moves through the uniform magnetic field, is exploited in a different setup that is called the vibrating sample magnetometer. A different approach exploits the effects to which a magnetic dipole, as a first approximation, the magnetization of the sample, is submitted when a magnetic field is applied. If the magnetic field is uniform, a magnetic dipole is submitted to a torque that tends to align the magnetization so the dipole, to the applied magnetic field. Conversely, if the magnetic field is not uniform, then besides the torque that tends to align the magnetization to the field, the magnetic dipole is also submitted to a force that tends to move the dipole towards the region where the magnetic field is more intense. The torque of the magnetization into a uniform magnetic field is exploited in torque magnetometers and, more commonly, in ferromagnetic resonance experiments, where the magnetic anisotropy is measured. The force to which A magnetic dipole is submitted when inserted into a non-homogeneous magnetic field is instead exploited into a measurement setup that is called an alternating gradient field magnetometer. Different approaches involve instead the identification of the domain patterns of the materials, so the identification of the direction of the magnetization in the volume or at least at the surface of the sample. A very common technique is the magneto-optic technique, also called Kerr effect. That is a microscopic technique where a polarized laser light is exploited. When the laser light interacts with the magnetization of the sample, its polarization plane rotates. So if you can analyze the direction of the light that is reflected by the sample and compare the polarization angle with respect to the incident light, you have an information on how the magnetization is oriented under the laser spot. Another method to image the magnetic domains of a sample consists in putting on its surface a so-called indicator film, that is a magnetic material that is very soft, meaning that it can be easily magnetized by the fringing fields emerging from the surface of the sample, and that also has an excellent magneto-optic response, or even a response that can be seen by the naked eye. In this way, it is possible to identify, by a contrast of colors, the different orientations of the magnetization at the surface of the sample. Other imaging methods of the magnetic domains involve more advanced scanning probe microscopy techniques. One that is rather commonly available is magnetic force microscopy, where a silicon cantilever ends with a silicon tip that is magnetic coated. And since the magnetic coating is polarized, meaning it is a sort of a dipole, magnetic dipole, its fringing fields interact with the fringing fields generated by the surface magnetization of the sample. By measuring the way the cantilever is affected by this interaction of fringing fields, it is possible to reconstruct an image of the magnetization distribution at the surface of the sample. Another similar technique, meaning that it is a scanning technique, instead of using a magnetically coated tip, uses nanodiamonds with a particular microstructure where a nitrogen vacancy generates an optical transition that is sensitive to the magnetic field. Again, the nitrogen vacancy is placed in close proximity of the surface of the sample, and the fringing fields generated by its magnetization are capable of affecting the optical transition. If that transition is measured, again, you have a means of imaging the magnetic configuration of the surface of the sample. There are also many other approaches that can be used to determine the magnetic properties of samples. For example, most magnetic materials are magnetostrictive, meaning that when submitted to a magnetic field, they change their size along the direction of application of the magnetic field. So a measurement of size of the sample under a magnetic field is a way to assess its magnetization. Other techniques involve resonance processes, like ferromagnetic resonance and the techniques based on vector-nectar analyzers. The sample is irradiated with a high-frequency electromagnetic field, typically a microwave, and an absorption spectrum is recorded. That is a function of the magnetization of the sample and of its magnetic anisotropy. Also, one can use thermal techniques. First of all, because a magnetic material that is doing a hysteresis loop dissipates energy in form of heat, and so a temperature increase of the sample is an indirect way to measure its magnetic hysteresis. But also there are calorimetric techniques that measure the differential calorimetry when a sample is compared against a known standard due to magnetic transitions. Since the magnetization involves ordering or disordering of spins, it is associated to a latent heat that can be measured. Then, of course, at a very small scale, newtons can be used to explore the magnetization of a material because neutrons have a spin, so have a magnetic property, but they are electrically neutral, so they do not interact with the electrons. Then there are also high-energy X-rays techniques that are similar in a sense to the magneto-optic Kerr effect, where polarization directions of a light, that in this case is X-rays, is affected by the magnetization of a material. These require the use of synchrotrons, and these techniques are extremely powerful because they are sensitive to individual elements of the material, so they are element-based. They offer element-based resolution. It's now time to describe more in details a few measurement techniques of magnetic properties, starting from those based on closed magnetic circuits. As we said, the closed magnetic circuit configuration has the advantage that the internal field is equal to the applied field because there is no demagnetizing field inside the sample. The disadvantage is that you cannot use any sample shape. The sample must have a shape appropriate for doing a closed circuit, and you have a limited choice of measurement types. The first equipments that we are going to discuss are the so-called BH loop tracers or wattmeters that exploit the Faraday-Neumann lens law. We are talking about closed magnetic circuit configuration. We have three different ways to obtain a closed magnetic circuit. In the first approach, the sample itself makes a closed path. This is typical of ring samples. Rings are normally made for ferrites or even with amorphous ribbons. There's also another way, a second way to make a closed magnetic path using just the sample, that is the one exploited in an Epstein frame. The sample is cut in slices with a standardized shape and size, and the slices are placed in a square configuration overlapping at the angles so that a closed magnetic path is made. A third approach consists of clamping a single sheet of a magnetic material into a yoke that is made of ferromagnetic material that ensures the closure of the magnetic path. In any case, in order to exploit the Faraday-Neumann lens law, the measurement is done in a time-varying condition, meaning that the magnetic field is generated normally by a set of coils that are powered by a sinusoidal current, generating a sinusoidal magnetic field. Another set of coils, called pickup coils, are wound around the sample or a portion of the sample and detect the electromotive force generated by the variation of the flux due to the variation of the magnetization of the sample that is submitted to the sinusoidal magnetic field. As long as the applied magnetic field is time-varying, it is not necessary that it is sinusoidal. For example, when magnetic losses must be measured in these materials, it is important that the induction of the material, so its magnetization, is sinusoidally varying with time. But since the relationship between the magnetic field applied and the magnetization of the sample is nonlinear, having a sinusoidal induction requires a magnetic field, an applied magnetic field, that is not sinusoidal in time. Through proper feedback mechanisms and using a programmable voltage source, it is possible to configure the experiment in order to have a sinusoidal induction to measure power losses in these materials. In principle, BH loop tracers and wattmeters are relatively simple setups that can be custom built in the laboratory, needing just a programmable voltage source, a power supply, and an oscilloscope in order to be able to do these measurements. Epstein frame and the shingle sheet test measurements are standardized into an IEC international standard. Another closed magnetic circuit setup that exploits the Faraday-Neumann lens law is the one used in permeameters and also called the ballistic method, that can be used with bars, rods, and thick specimens that cannot be used in Epstein frames or single-sheet testers because of their shape or volume. The idea is once again to clamp the sample into a magnetic yoke to ensure a closed magnetic path. The magnetic field is generated by a set of suitable coils, and again, coils wound around the sample are used to exploit the Faraday-Neumann length law and measure the induced voltage. In this case, however, the applied magnetic field has a different time profile. The measurement is done with a point-by-point procedure. The magnetic field strength is changed in a step-like fashion, and during the transient from one constant field values to the subsequent one, the secondary coils pick the induced transient voltage that is integrated by a flux meter. As an alternative, the magnetic field strength can be changed in a continuous fashion, but slowly, in order to avoid eddy currents, because these samples are thick, are massive, compared to the ones used in Epstein frames, for example. The secondary winding, therefore, picks a slowly varying continuous signal that again is integrated by the flux meter. Using pickup coils of calibrated cross-section, it is possible to measure the magnetization of the material as a function of the applied magnetic field. A ballistic equipment is somewhat more difficult to build in the laboratory. Again, a programmable DC power supply is needed, but also manual or programmable circuit inverters are needed, or breakers also. A Gauss meter is required to measure the applied magnetic field, or a voltmeter if the current flowing in the primary winding is measured. And then the most important piece of equipment in this setup is the flux meter. Toroidal samples, for example ferrite rings, can also be characterized at higher frequencies using vector-nectar analyzers. We are talking about frequencies that can go up to the gigahertz region. A coaxial line short-circuited is exploited in this case. The sample is placed as the dielectric at the end of a coaxial line close to the short circuit. In that condition, the electric field is minimum and the current is maximum, meaning that the sample is submitted mostly to a magnetic field with maximum intensity. The magnetic field is circularly polarized along the path of the measured ring. The measurement consists in sending an electromagnetic wave to the coaxial line. The frequency of the electromagnetic wave is swept between a lower and an upper limit. The short circuit reflects the electromagnetic wave, and the amplitude and phase of the reflected electromagnetic wave is measured with respect to the incident wave. Since the electromagnetic wave passes through the sample, its properties are affected by the frequency-dependent permeability of the sample itself, both real and imaginary part. The complex magnetic permeability of the sample can be calculated by a proper difference between a measurement done with the sample inside the measurement cell and the measurement cell without the sample inside. Let's now discuss measurement methods in open magnetic circuit configuration. As we said, this configuration has the advantage that you can use samples of any shape, although not of course of any size, and you have a wide choice of measurement types. The disadvantage is that it is not easy to know the internal field of the sample, because the calculation of the demagnetizing fields is not possible for an arbitrary sample shape, and numerical methods must be used in that case. Even though we discussed them in the closed magnetic circuit configuration, BH loop tracers can be used also in the open magnetic circuit configuration, again exploiting the Faraday-Neumann length law. The technique consists in using two nominally identical coils. One is the sample coil that is meant to host the sample. The second one is the compensation coil that is counterwound, so that when no sample is present and an alternating magnetic field is applied, the total electromotive force will result to be zero. Instead, when the sample is inserted into the sample coil, its presence will unbalance the set of the two coils. Its flux variation will induce an electromotive force that is due only to the cross-section of the sample and not the one of the coils. In order to measure the applied magnetic field that is applied through an additional coil that is placed outside both the sample and the compensation coil, either a Hall probe is used or a search coil. All the signals as a function of time are acquired with an oscilloscope and then integrated in order to reconstruct the BH loop. A widely available technique for the characterization of magnetic materials in the open magnetic circuit configuration is the vibrating sample magnetometer. Again, it exploits the Faraday-Neumann-Lenz law, but in the second case, the one of a uniform magnetic field and of a relative movement of a coil with respect to the applied magnetic field. The sample is attached to the end of a rod that is vibrating close to a set of pickup coils. In the simplest case, there are just two to the left and right of the sample, but in more complex cases, they can be four or even more. When the sample is magnetized, either spontaneously or by applying a magnetic field, the fact that it moves with respect to the coil induces an electromotive force on the coil themselves. This electromotive force can be acquired, filtered, for example, with a lock-in amplifier that is locked to the vibration frequency of the sample, and compared to the signal given by a reference material of known magnetic moment. In this way, for any given applied magnetic field value, the magnetic moment, in fact, of the sample can be obtained. Normally, in a VSM, the magnetic field is generated by an electromagnet. This means that its direction is perpendicular to the direction of vibration. However, if the magnetic field is generated by a solenoid, then the pickup coils are placed along the direction of vibration, and the geometry changes a little bit, but the way the system performs is the same. The condition where a solenoid is used is typical of squid magnetometers that can operate often as vibrating sample magnetometers, but with a different principle for sensing the signal coming from the pickup coils. Alternating gradient force magnetometers instead use the force to which a magnetic dipole is submitted when inserted into a volume of non-uniform magnetic field. In order to generate a non-uniform magnetic field, that is, a field with a gradient, first of all, a uniform magnetic field is generated with an electromagnet. Then, on top of that, two coils are used no longer as sensing coils, but as active coils. They are driven with different current intensities so that they overlap to the static magnetic field generated by the electromagnet, a non-uniform magnetic field, giving a gradient. The sample is suspended into that gradient on a rod that ends with a piezoelectric bimorph. In this way, when the sample is submitted to the force that moves it towards the region where the magnetic field has strongest intensity, the piezoelectric bimorph will respond with a voltage that can be measured, amplified, and again compared with a signal given by a reference material in order to be able to determine the magnetic moment of the sample. The measurement is done in a point-by-point fashion, so the static magnetic field is applied at a set of different predetermined values, and when that field is constant for each value, the gradient is applied. To increase the sensitivity, the gradient will alternate in time from in one direction and the other, so that the signal coming from the piezo biomorph will be also alternated in time, and that is the detection, the amplification, and the filtering of the signal, again by means of a lock-in amplifier, in order to have better measurements. Another common method that is even standardized in the same IEC standard discussed above is the so-called extraction method that again exploits the Faraday-Neumann length law, but in open circuit configuration. Here again, two identical coils are used, immersed in the same applied magnetic field. But in this case, the sample is moved from one coil to the other and the other way around. The differential signal picked by the two coils is then amplified and integrated in order to calculate the magnetic moment of the sample as a function of the applied magnetic field. Ferromagnetic resonance techniques, instead, use spin precession phenomena. The sample is placed on top of a coplanar waveguide that generates a microwave magnetic field that excites the sample. Its magnetic permeability, its complex magnetic permeability, is responsible for a variation of the transmission properties of the waveguide that can be measured again by a vector network analyzer. In this way, absorption peaks that are due to ferromagnetic resonance can be measured as a function of frequency and of the applied magnetic field. In order for these measurements to be effective, the sample normally is a thin magnetic film, the surface must be very clean, and the sample must have a relatively strong magnetic anisotropy. Magneto-optical Kerr effect microscopes, as we discussed earlier, consist in sending a polarized light to the surface of the sample and detect the angle of rotation of the reflected light, of the polarization of the reflected light with respect to the incident one. That angle of rotation is proportional to the magnetization direction and relative intensity of the magnetization in that point of the material. Normally, the technique consists in acquiring images of a whole field of view as a function of a magnetic field that varies in time. Then, either the images provide the time evolution and so the field evolution of the magnetization of the sample, or they can be used to calculate the average magnetization over the field of view by assigning proper values to the gray levels corresponding to clear and dark domains that are oriented along different directions. In this way, the hysteresis loop of that specific region that is illuminated by the laser spot can be reconstructed. Magnetic force microscopy is another imaging method that gives you a representation of the magnetization of the sample, at least at the surface of the sample. However, it does not directly reproduce the magnetic domains of the sample. In fact, as we discussed, this technique works by making interact the fringing fields at the surface of the sample with the fringing fields at the magnetic tip. This means that the oscillation of the cantilever is a function of the double derivative of the z component of the field of the sample with respect to the z direction 2 times. This means that this imaging technique that is sensitive to the magnetic charges at the surface of the sample and not directly to the magnetization, only gives an indirect representation of the magnetization that must be interpreted by an experienced user. The magnetic domain configuration can be studied with the MFM at different applied magnetic field values, at least for applied field's intensity that do not perturb too much the magnetization of the scanning tip. Inferring the actual magnetization value of the sample is quite difficult. Quantitative magnetic force microscopy is indeed possible, but it requires a careful magnetic characterization of the tip that is extremely difficult to do, and that must be repeated every time the tip is changed or its properties evolve as the tip wears out with usage. Quantitative measurement of the magnetization of the sample is somewhat easier with NV diamonds magnetometers, so NV centers in diamonds, as these centers are absolute magnetometers. When the magnetization of the sample has suitable characteristics, it is possible to do imaging with a magnetic force microscope, not at constant magnetic field, but at varying magnetic field. The idea is that an image acquired by a magnetic force microscope is made of several different lines that normally reproduce the magnetic domain configuration over a certain field of view. However, it is possible to disable the scanning of the magnetic tip in one direction in order to repeat the scanning of the same line over and over again. If the magnetic field, the applied magnetic field is synchronized with the scanning of the microscope, each line will be acquired at a different magnetic field value. And this way, it is possible to study the evolution of the magnetization along that line in a single image for a given magnetic field history. The techniques that we briefly discussed in this video are not the only available ones to measure magnetic properties of materials. They are just what they are normally the most widely available. The take-home message is that when you can, use a closed magnetic circuit configuration, because the absence of demagnetizing fields makes your life much easier if you want to know the magnetic field that is inside the sample. But when you can't stick to a closed magnetic circuit configuration, normally because the sample shape does not allow you to, then try to use, if you can, a magnetometer, for example, a vibrating sample magnetometer, because it is sensitive and it is very versatile. However, keep in mind that normally you will almost never measure the magnetization of the material, but only its magnetic moment. This means that you will almost always need to know either a cross-section, a mass, a volume, a density, some of these properties of the sample, in order to obtain the magnetization. And unfortunately, this property that you need to know to convert the magnetic moment into the magnetization is the one that normally has by far the largest source of uncertainty.